Hello and welcome back to compiler programming. In the last video, we implemented this program end call that allows us to defer the encoding of the function till the point in time where we do call this function. And now it's time to take another step in unifying how we handle the creation of executables and how we handle the creation of this JIT code that we can call directly from the tests. And the idea that I have is to make this final call the thing that returns you the value that you want. So you would always sort of have this program abstraction. You would do stuff and you would put functions, you would put global data, whatever you want. When we implement the parser, we could like call the parser and use it here or something like this. And then at the end, you make a decision. You either create an executable out of all of this, or you're gonna create a JIT program that you can call right away. This change will require tweaks in quite a few places, but we can start with that right now. The main idea here is that I would introduce a new concept, which would be, I guess we'll call it JIT program or something like this, JIT program. And this JIT program will have a different setup from the regular one. Actually, some of the stuff from the regular program will be moved into JIT one, and some of the stuff will be done differently. So the first thing is this function buffer. I already mentioned it in one of the previous videos that I want to get rid of it in the program because it doesn't make sense really for the executables. We will keep the data buffer, although it might also change its shape at some point. And next, we will get rid of this function builder as well. And or actually, no, we'll leave it here, but we will get rid of it in the JIT. And in the JIT, we will have something like buffer, code buffer. Okay, that is good. And we will not have functions anymore, I guess. We will need to have a way to look up the pointers to actual functions through some means. So I guess we will have a map here, or for now it can be just an array. It doesn't really matter what we use. But this can be added later. And here we also don't need these two files. Okay, so this is what JIT program will be for now. And maybe let's add this type def array type of value star array function values, or array value pointer. I don't know how we want to deal with it. Let me find where our value is defined so that's nice and neat and we don't have it spread all over the place. Okay, so this should go into here. And now we can say that this is in reality, it's actually not going to be array of values, but rather it will be a special construct that will be something like name and value. Or thinking about this now, we could keep the currently used values and keep them working. Yeah, I think that is probably fine as it is right now. Let's just start with this code. Okay, so we have a bunch of things that we need to think about. First one is this free buffer of function buffer. It doesn't exist anymore because this was previously used for the machine code, both in the case of JIT and in the case of executable. So as you can see here, for JIT we would do this make buffer with page execute write. I will for now remove this stuff and maybe put it in the comment here because we will need to pick it up a bit later. And this buffer also will be able to use more standard memory allocation later, and maybe even turn it into something like a bucket buffer that allows us to just do less of reallocating memory, which is going to be good for speed eventually. Okay, for now we can get rid of this stuff and see what else is a problem. Okay, here is where we keep the pointer to the buffer inside of each function builder, which is no longer technically necessary because right now we are not doing the encoding as we go, and that means that when we call program end is where we actually need those buffers. So let's get rid of this, let's get rid of this. We also need to get rid of function builder, so of a buffer inside function builder. So this buffer goes away. This will cause other problems, of course, but this is exactly what we are doing here. Okay, so the first thing here is now we need to pass a buffer to encode instruction directly. So this no longer is attached to the function builder. It is a more global buffer that we have to somehow deal with. And it creates a bunch more errors that we can go through and start dealing. Okay. We have this function encode. Now this function encode also needs to have a buffer. And we need to pass that buffer to the right call. Okay, that looks good to me. And we also need to figure out a buffer here. Now, here I will not pass in the buffer, but rather I will create one right away. And instead of void, this thing will now return a JIT program. Okay, so we say JIT program result is this stuff, and this is where I will come back and pick up this function buffer from here, so we no longer need to have executable thing here. We can get rid of it here, and we can put it over here. Okay, so code buffer is this stuff. Next thing is data buffer. We are just gonna steal it from program. So program data buffer. This is fine. And we can now pass this buffer to function encode. Result code buffer, like so. Cannot convert from buffer to buffer star, so we do it this way. Okay, and we can return result. Good. One thing to think about here is we need to figure out how much memory we actually need to get all the instructions in, because right now we just have this fixed size buffer, and if you have a very long program, eventually it will run out, but there is something that we can do which we can maybe take a look later in the episode. Okay, fix me adjust the size of the code buffer dynamically. Okay, that sounds good. Function buffer is not a member of function builder. Okay, what are we doing here? Well, here we are checking the relative virtual address of our base code compared to the data stuff which we use for reparative address calculations. So this code will now have to go into the program end, and I guess we should get this fits into S32 as well. So what we are doing here now is saying that program code base RVA is this stuff. Program. So instead of program function buffer, we are using result code buffer. Yep, and this thing and this thing. Left the data library, the data buffer must be struct union type. So you're not happy with the program? That's strange. Okay. Buffer is not a member of function builder. Indeed, it isn't. So we can probably just remove this stuff. Yeah, I guess this shouldn't be necessary now. Instead, when we call function in code here, we will need to pass in the buffer function. Yeah. Okay, we have predefined function in code. I guess we have done it over here. Yes, so this needs to now accept pointer to the buffer. Yep, and it will be exe buffer. Okay, we are building something. Let's see if that something makes any sense to the system. Okay. So in general, it seems to be working fine, but there is this assertion failure in one of the tests. Namely, I believe it is this one. Yeah, so something with reparative addressing is not working exactly right. Let's take a look at what is going on in value global. So I will need value.c and let's look at what this does. Okay, so we are allocating some size in the data buffer. Okay, that makes sense. And then we are storing this address as an immediate. Okay. I think we will also have to change how reparative works in a bit, but I want to try to first make it just pass as it is at the moment. So let's open up our Visual Studio to see where the problem actually is. Okay. And let's just start this. Okay, yeah, because this file passes just fine, but we want to try to run this file. Okay, so you are failing over here. And you're saying that, what is this? What is diff? Well, that is fine, I guess. What is it? FA, FF, C4. Yeah, this is actually okay diff, but the way I'm comparing here is obviously not okay. I believe I actually have a function for this now, so we can try to use that thing instead of previous code. So we are here, and I can do assert fits in, I think it's called fits in something, fits into, yeah, fits into S32 of diff. Okay, let's see if this is better. And if you're curious, the way this function works is that when you have a signed number, for example, you have an 8-bit signed number, you remove one bit because that bit is responsible for plus or minus sign. So you actually have like 7 bits of number itself. And in the negative numbers, you have one more number. So you don't have -0 in integers. That means that you can encode one more number in negatives rather than positives. So in negatives, you have the full 2 to the 7th power here, and here you have 2 to the 7th power -1. And the way that it works out is, for example, if we go to say 1 to 7, this is 128, right? And if we have a byte, it goes from -128 to 127. And this is exactly what we're having here. So 1 shift 7 is going to be 128, so -128. And value here is going to be 128 minus 1, which is 127. So this just checks the bounds. And technically we can put any bit in here. So if you wanted to have like fits into S16, we can also very easily do that. We would just put 15 over here and 15 over here, right? Okay. Let's see if that does anything though, because it might not. And it actually does. So we successfully changed the way the encoding works and where it is stored. Right now we are creating one buffer for all of the code, and it's done at the very last step right here. Okay, we also have this fix me about S32 here, so let's deal with that as well. Let's say that S64 diff is this, and then we do assert fits into S32 of diff, and then we can cast. Maybe I should have something like saved truncate to S32, so I don't need to do it in 2 steps, but for now that's fine as well. Let's recheck our tests. Okay, still works like a charm, so we can remove this fix me from here. Okay, one final thing I want to do now is deal with this dynamic sizing, and there are essentially 2 ways how we can approach this. As I talked about in my data structures video, which I can link in the description, you basically should decide if you can figure out some kind of upper bound for the allocation that you need, and if you can do that, then generally it's a good idea to do so. Otherwise you need to size dynamically. For for this stuff, because we know that this is machine code, and because we know how many instructions will be there in the machine code, and we know that on x86 the size of the single instruction is no bigger than 15 bytes, we can just use this to do a conservative estimation of the maximum buffer size that we will need to encode this buffer. So let's try to make that calculation. So we say U64 and say estimate max code size, and we pass in, let's just say we pass in program star program. Okay. What will this do? Well, it needs to go through all of the functions like so, right? And then it needs to figure out what is the total count of instructions. So we say U64 is total instruction count is 0. And here we just say instruction count plus equals array, I don't remember if it is size or length, but we can check array size of I guess this will be builder, and then instructions. Yeah. Builder instructions. Okay. Okay, it's not array size. I guess it is array length. It's not array length either. Then it must be array count. Okay. Good. Return total instruction count times max bytes per instruction. And we have max bytes per instruction is 15. We can actually verify that. If Firefox opens, let's say x86 maximum bytes per instruction or something. Maximum bytes per instruction. That sounds good. Requires at most 15 bytes, and it is for this move ups instruction. So yeah. Well, this is not really true. I think the instruction decoder will be pretty angry at you. Yeah, 15 bytes is the right answer. And we can do this should be architecture dependent. So if we ever decide to do ARM version of this will need to change. But for now, this makes sense. So this needs to be const 64. And we are good to go. Okay. Max code size in bytes. Cool. Well, now we can say U64 code buffer size is estimate of program. And we take this and we do this. And we can also align it just to have some space. Or actually, we don't need to align it because the system will do it for us anyhow. Okay. And we can printf what is the number we came up with here. %lu code buffer size. Let's just do /n, something like this, so it's more visible in the output. Okay, let's see if this is good. Okay, so our tests seem to pass, and you can see that we have quite different number of bytes that we have reserved here. Fibonacci numbers is probably our biggest function, so you see we have quite a few bytes reserved. We can also check what is the occupancy of this stuff, so we can say reserved, and we then say occupied LU, and we say result code buffer occupied. Occupied is not a member of buffer. Or is it not? Let me check real quick. How is it called? It is a member of thing. Maybe I just misspelled. Yeah, because it's called occupied, not occupied. Okay, let's check what that results. And here we see roughly the distribution. And depending on the program, it is a bit more, a bit less, but roughly it is half. So if we want it to be like fancy, we could say, okay, we take the 15-byte maximum and we estimate that it's going to be on average, I don't know, 70% if you wanted to save some memory. But honestly, I don't expect that majority of the programs will be gigabytes in size. So this is probably okay if we have on average twice as much memory as we actually need. At least we know that we only have one allocation. We know that we will never run out of memory, and this is pretty neat. I think that will be it for today. Thank you very much for watching, and see you next time.